Okay, I'm going to make the model a little more complicated. And the way that I'm going to do that is I'm going to keep this same ideas of sunlight coming in, striking a circular surface, and then black body radiation being radiated away from the Earth. Uh, but instead of just setting those equal, what I'm going to do is I'm going to say that the Earth is made of a thin layer of water. And what's happening as the sunlight comes in, it is going to warm the water. And the water then, as its temperature changes, begins radiating the heat away. And so then we're going to have a slightly different balance because, as you'll see, if we assume this water is warming up, we have to think about how to solve this problem a little bit differently. So what I'm going to do is I'm going to assume there's a water layer, and the water layer is on the entire surface of the Earth, and I'm just going to start with a depth of 2,000 meters. I think that's a little over a mile deep. So, some of the oceans are very deep, some of them are shallow. We'll assume that this is reasonable, and you can try to see what happens if you change the depth. How does that affect the temperature of the Earth? So I'm going to start with that. That means that if I want to calculate the volume of water, I can do that as the surface area of the Earth, which we saw in a previous video, is 4 pi times the radius of the Earth squared, and then I can multiply that by the depth of the water to get a volume instead of an area. And if I calculate that, I get a really, really large number. That is going to be equal to, so these numbers, 4 times pi, the radius of the Earth is 6.37 times 10 to the 6 meters, and I square that, and then I have a depth of 2,000 meters. So that number, when I calculate it, is 1 times 10 to the 18. So that's 10 to the 18 meters cubed. And what we can do is we can think back to our knowledge of water. For water, we know that water is 1 gram for 1 milliliter. That's the density of the water. And if I want to convert that, because eventually I'm going to want kilograms in order to use my normal units that we use. So that would be 1,000 grams for 1 kilogram. So I can cancel the grams. And then I would multiply by 1,000 milliliters in 1 liter. And my milliliters will cancel. And then I can multiply by 1 liter is 0.001 meters cubed. Because 1 liter is 10 centimeters by 10 centimeters by 10 centimeters. That will give me this number. And so if I calculate that, then I'll get that there are 1,000 kilograms per meter cubed. And so if I take that number and I multiply it by this volume, my meters cubed will cancel. And so I have 1,000 kilograms per meter cubed times 10 to the 18 meters cubed. My meters cubed cancel. I get 10 to the 21 kilograms of water. So that 2,000 meter deep layer of water on the Earth corresponds to 10 raised to the 21 kilograms worth of water. Why do we care about that? because if we think back to the energy required to warm water, we have this heat equation that says the mass of the water times the specific heat or the heat capacity times the change in temperature is the energy to change the temperature of water. So we think back to our model for the sunlight and the blackbody radiation that's leaving. What we know is that we have power coming in from the sun. We have power going out, and so the total power that there is going to, what we would call the net power, is just the difference between what's coming in and what's going out, and that's equal to the energy per time that's striking the earth and causing the water to warm. So if I take this energy per time, I can, if I just multiply by some amount of time, so if I say P net times a change in time, that will be set equal to this heat, but that heat is related to a change in temperature. So if I write down everything that I know, P net is going to be pi r of the earth squared times S minus 4 pi r squared E sigma t to the fourth. And that's going to be equal to mc delta T. And so now I have, not only do I have an equation where there's temperature in it, I also have an equation that has the change in temperature in it, and that's kind of complicated to think about. So we're going to see how to apply this and make calculations, but since we have a change in temperature, what we have to do is we have to break this into pieces, begin from a planet that is at 0 temperature, allow the sunlight to come in, and then slowly warm it up by taking very small steps. And I actually left a very, very important piece out here. So I have this P net I forgot to multiply by a change in time. Okay, and so what I'm really going to want to know is what is the change in temperature, and so what I'm going to do is I'm going to divide both sides by mc, and so what I'll have is that my change in temperature is equal to everything here in parentheses multiplied by the change in time divided by the mass of the water and the heat capacity of the water.